All right, here we go. Some examples of limits. This is number 1 of the textbook, page 48. Well, if you notice, there's no domain issue with 3x minus 1. It's a linear function. Polynomials don't have any domain issues. So, if you can do a straight plug-in right off the bat, then do it. It's -7. So the limit doesn't have to be like a circle, like an open circle, or some kind of weird, funky domain issue. You can find the limit as x approaches any number, and it can exist at a certain spot. Check out number 7. Pi? Well, think about it like this. What does the graph pi look like? It's a constant value, 3.14 ... So here's 1, 2, 3, 4. It's like a horizontal line that is, steady Eddie pi units. Always pi. So the limit as x approaches -1, the y value is pi. Interesting. You can think of it too as there's no domain issue. So wherever you see an x, plug in a -1. When there's no x to plug into, then whatever that is there, that's your solution. Not really a solution, that's the value of the limit. All right, so hopefully we're getting like a clearer understanding that, hey, a limit equals a y value. A limit is the x approaching some number to get a y value. So when you look at something like this, you're thinking to yourself, all right, here, we finally got the domain issues floating around, right? But is that the domain issue? I mean, we have a domain issue. It's all reals except x can't be -1/2. If this limit does not match the domain issue, just plug in. Yeah, you're okay. Plug in a -1, +4. Plug in a -1. You get 3 over -1 plus 1. Not -1 plus 1. -2 plus 1. I'm sorry. It's been a long day. It's been a very long day. But yeah, -1 ends up being the sum on the bottom. And okay, -3, got it. So do you get that you're looking for domain issues? And if you don't have them, plug in. Wait, can you guys see that whole thing? Yeah, you got it. 21. I'm not restarting this video. H cubed plus 8 over h plus 2. Now this is something you guys haven't probably seen since Math 3. I don't know, maybe I threw it at you in pre-calc, but a cubed function added together has a certain formula to it, and I you know what? This is a good time to revisit that. So what does h cubed divided by h plus 2 look like? Well, you can actually derive the formula for h cubed plus 8 factored by doing long division. I think synthetic division is another thing you guys may have done in the past, but I'm just going to show it using long division. So what we do is we say h cubed plus 0h squared plus 0h plus 8 is an equivalent polynomial to h cubed plus 8. So now you say, how many times does h plus 2 go into h cubed plus 0h squared? Well, it looks like we need to create an h squared to cancel with that h cubed. So h squared times h is h cubed. H squared times 2 is plus 2h squared. You know how dividing works, right? You subtract it. 0 minus 2 is negative 2h squared. Then you drop the next digit of accuracy. We need a minus 2h to cancel with this. So negative 2h times h is negative 2h squared minus 4h. So these cancel. 0 minus negative 4 is positive 4h. Plus 8. This is exactly 4 times that. So what we did there was we just factored the polynomial h cubed plus 8. It's the factor h plus 2 times h squared minus 2h plus 4, which, incidentally, if you got a cubed plus b cubed, this kind of mirrors the formula. This is h, this is 2, right? 2 to the third power is 8. It's a plus b times a squared minus the 2 multiplied together. Where'd the 2b come from? That's an h. Ugh. Oh my goodness. All right. So really this isn't new calculus type stuff. I was just kind of like rehashing this whole idea of, hey, there's a formula for factoring perfect cubes added together. And this is how it's generated. And you didn't see the last part of that, but I think you got the idea. So the limit as x approaches negative 2 of this original can be rewritten as h plus 2 on top times h squared minus 2h plus 4 on the bottom. And then h plus 2, of course, it's not equal to, it is the limit of that. Cancel those out, and you should be free to plug in negative 2 into a polynomial because a polynomial has no domain issues. Squared minus 2 times negative 2 plus 4. 4 plus 4 plus 4. 4, 8, 12. Yeah, so besides all of this, it's pretty straightforward, right? Can you factor? Can you recognize when to just do a straight plug-in? Did you make sense of the root and the factoring equations from the one examples I did before? And here's the last one. This one, I think kind of requires you to think in terms of graphs a little bit more so on 25 and 29. This one wants you to compute the limit as x approaches 4 from the, I can't remember what the order was, left, right, and then at that spot. So 4 from the left of f of x, 4 from the right of f of x, and then just at 4. Oh, you know what? We can talk about absolute values as piecewise first, maybe. Instead of just kind of randomly grappling with the graph like plug in this, plug in that. Although, let's do one where we just plug in x values and see what the y values come out to be. So plug in 0. The absolute value of 4, 0 minus 4, negative 4, absolute value of that is 4. Here. I'll come closer. This equals the absolute value of negative 4 over negative 4, which equals 4 over negative 4. It's negative 1 at 0. Try 1, right? 1 minus 4 over 1. Oh, I see what's happening here. Pattern. Yeah. They're going to be negative 1. So Yeah. 0's -1, 1's -1, 2, 3. When does it end? It ends at 4. At 4, we have an issue. You can't plug in 0. And what happens at 5 is plugging in 5 on the bottom and 5 on the top always creates positives. So it's +1 from 5 to infinity. 1, 2, 3, 4, 5. And I would assume that any even small number above 4, like 4.0001, that's got to be a tiny, tiny number that matches the tiny, tiny number at the bottom. So it's basically going all the way to 4, and then it doesn't quite pay off. Same thing here. So those are open circles that I don't think you guys can see too well there. But that's interesting. Because usually the open circles converge to one spot. In this case, they're not. So when you think of what's the limit as x approaches 4 from the left, it's -1. When you think of it as 4 from the right, it's +1. So what's the limit going to be at 4? Well, the definition of the limit actually is that the left must equal the right. If they don't, it doesn't exist. It doesn't exist. All right, last one. I believe it was 0 was the approach. Yeah. So 0 from the left, 0 from the right, and 0 itself. Let's check out the graph. So this is 1x times 1x times 1x. We have to have an asymptote at 0. So just pretend like that's an asymptote. What's it look like coming from the right? Well, from the right, 1 is 1. Right? If I plug in 1, I get 1. But once I start plugging in small, like bigger numbers, like 2, I'm cubing 2 now. So it's 1/8. That's like that's 1/8 of a block. And just think about it. Then I plug in 3, it's at 1/27th. I plug in 4, and it's at 1/64th. I plug in 5, and it's 1/125. Not hugely, really small numbers that are just above the y-axis, the x-axis. Conversely, when you plug in numbers that are between 0 and 1, like a half, it's dividing by 1/8. So it's 8. We're climbing up quickly is what I'm saying. So actually, I know what it is from the right. From the right, it's approaching, whoa, positive infinity, never going to cross that asymptote. So we got infinite values right now. What's going on from the left? Well, when you plug in -1, you get -1. And then all this business reverses its course. So -2 would be 1 over -2 times -2 times -2. Multiplying a negative number times itself an odd number of times yields another negative value. So we're never crossing the x-axis. The x-axis. It does this. From the left, you're going to negative infinity. Yeah, you didn't see that, but I wrote negative infinity. And then at the point itself, you're not going to find a limit. It doesn't exist. All right, guys. I think I found my threshold for making videos. I'm going to stop here, and yeah, the next video will be better for sure. So hopefully this was helpful, and you guys know exactly what to do to tackle this first real calculus assignment.